everyone. Good morning or good afternoon if you're on the East Coast. And thank you very much for attending the 70th Q-Chem webinar, which is going to be from Jonathan Wong. And just a quick bit of information about him. He received his BA in chemistry from Cornell University in 2017. And he went on to do his PhD in chemistry at UC Berkeley, where he was advised by Professor Martin Head Gordon. And he's done a great deal of work in that group with NMR shieldings, and he'll be discussing some of that work today during his talk. And he's contributed a lot of really nice features to the Q-Chem source code, and he completed his PhD in 2023, so just this year. And he is currently working as a researcher at Amden Inc., exploring designer AI and its computational chemistry applications. So thank you so much, Jonathan, for being willing to give a talk, and I'm very much looking forward to hearing about the work that you've done. So thank you. I'll go ahead and hand it over to you now.
Yeah, well, thank you, Sharon, for the nice introduction. And hello, everyone. I'm Jonathan. So today I'll be talking about calculating NMR shieldings with GIAO, specifically a method-independent approach that we recently added to the 6.1 release. Right, so to outline, I'll go over some things about properties calculation, the few Hamiltonian new matrix elements that we added to Q-Chem, numerical accuracy of our methods, so a quick guide on how to run these jobs, and then a few examples. Right, so before I start, I want to acknowledge people who contributed to this work. So Brett Gano and Tim Neudecker, they sort of started this project with me. Xiao Liu, he helped me a lot recently with debugging this code and adding new features. Here goes, he's taking over my project since I graduated. Eric Berquist, who was formerly at Q-Chem, he assisted a lot in the code design integration. Jiazhu Liang, who did the DFT integration part of this code. Of course, Junho Lee, who did a lot of the. Yeah, so I guess we got through the acknowledgements, okay? So yeah, let's start from the top again. Right, so yeah, in general terms, we talk about molecular properties. So these properties are sort of defined by energy derivatives. So we have sort of different orders of these properties, first order, second order, and so on. So they're simply first order derivatives of the energy, second order derivatives of the energy. So now you can have sort of mixed derivatives of different external perturbations. So today we're talking about properties associated with a external magnetic field B. So when we think about a molecule sitting in this external field, its energy will change in response to this external perturbation. So just considering a closed-shell molecule, so we don't have unpaired electrons, this energy change is up to starts at second order, where we have two associated properties. First is the magnetizability tensor. The second is this nuclear shielding tensor. So the magnetizability tensor is associated with the molecule's energy change in response to the field only. Nuclear shielding tensor describes the molecule's energy change when the external field couples with the nuclear spins. So the second part is what the NMR experiment measures, and of course it's immensely useful for people doing experiments. Right, so the magnetizability tensor is defined this way. It's the second derivative of the external the energy with respect to the external field B. Usually you take the isotropic form, which is just the average of the trace. The shielding tensor is similar, where now you have one derivative, the B field, one derivative of the nuclear spin, denoted by this mk notation. Yeah, also it's usually presented in an isotropic manner, just due to the rotational averaging when you actually run the experiment in solution. Right, so when we want to calculate properties, there's two ways to go about it. The first way is the usual way, I'll call, is the response equations formalism. The second way is using a simpler finite difference approach, since we're taking derivatives of stuff. So let's first go over the first way, which is the response equations. So I first consider variational methods such as FCF or FUCI. Our energy, we can write that depending on two external perturbations A and B, and lambda, which is a sort of general wave function parameter. For variational methods, energy is a minimum at the optimal wave function parameter set, denoted by lambda star. So this will be useful property to use. So first order property is to take one derivative of the energy with respect to a single perturbation. Just simply taking the chain rule, we have two parts. One is just the original derivative. The second part is the chain rule part, where now we have this term, d lambda. But yeah, I guess start from here then. Just about Sharon, the spot.
Yeah, right about there.
Okay, yes, yeah. So, right, so for variational methods, calculating a first order property with the nice property or the nice result where we don't have to deal with the wave function response. So it's a relatively simple expectation value of the Hamiltonian derivative with respect to perturbation of interest. For a second order property, however, this is no longer true, which is this term is no longer zero. So now we can handle the d lambda dB term, which is the wave function's response to perturbation B. So this is, can be solved by solving this equation, where this double derivative of the E with respect to lambda is the electron Hessian. So one can invert this matrix C, multiplying to the right-hand side and get the corresponding wave function response. But of course, in practice, this is not actually done. These responses are solved iteratively using different response equation formalism, depending on the method you're using. So for non-variation method, it can be treated in a similar manner. Instead, now we're treating the object as a Lagrangian, where we have constraints on the wave function E and lambda prime, which is the corresponding Lagrange multipliers. So the second order properties using this sort of formalism, we get again the wave function response, d lambda dB. We also get the Lagrange multipliers response, lambda prime dB. So we have to solve for both of these responses to get our properties, which will give you a new set of equations here. Yeah, so what do we actually need to calculate properties using these first equations? First, we have to derive expressions for the response equations based on the method of our choosing. And we have to implement these equations and their solvers. We also need to implement these new matrix elements that come up from the derivatives. So this second part, the green part, is the same across methods. It's the first part that we need to do for each method that we're interested in. So in effect, we have this kind of workflow. We have the matrix elements that we implemented. Now to implement and derive these new response equations. And finally, we get our properties. Is the sound still working, Sharon?
It is still working. Yes, we can still hear you.
Okay.
Thank you for checking in.
Yeah, of course. Right. So yeah, so we have the usual suspect, Hartree-Fock and DFT. So the corresponding response equations, they're called coupled perturbed SCF equations. We also have the non-variational methods, or the NP class of methods, and a couple clusters. Correspondingly, we have the Lagrangian and the z-vector equations. And then a couple clusters, we have to solve the delta equations. Right, so you're obviously doing it the analytical way, right? It's nice on the computation. Of course, in contrast with finite difference, you tend to do multiple single point jobs, and then you have the issue of numerical accuracy. The drawback really is sort of from a developer standpoint. For each new method that comes up, you have to derive and code up these new response equations, add it into Q-Chem, and then you can get your properties of your new method finally. So that might take up a lot of time. Right, so we consider, right, yeah, so before I go to the next part, the current Q-Chem capabilities with respect to these magnetic properties, we have Hartree-Fock and DFT up to hybrid GGA and PV10 for non-local correlation. So you can use these to calculate NMR shieldings and the related J couplings, hyperfine interaction, and so on. And we have support up to H functions. So what we don't have is the methods in DFT and PPT, which is the MP class of methods, and CCMN2, which is the couple cluster class of methods. So the motivation for doing this implementation was to get those methods up and running for these class of properties and more. Yes, so for that purpose, we consider the finite difference way of going about the energy derivative. So what we need for this is a field Hamiltonian, evaluate energy from this field Hamiltonian, whereas there you have explicit dependence on the electric field, the magnetic field, and the nuclear spin, of course parameterized by the nuclear coordinates. So what we basically just do is run some single points, where, for example, for a single term in your second order property, we need 4 single point calculations for one tensor element. So this is up to sort of second order in the finite difference. So this is nice for properties related to fields because the number of single points does not scale with system size. Your field is always 3D. For MK is caveat where you consider a particular K. LK here is the nuclear index. So if you're just interested in a particular nuclei, this doesn't scale with system size. Yeah, so this is nice because we can always just do 4 single points and get a property, even if you have a huge molecule. Right, so yeah, this approach, in effect, we have to implement these new integrals, which I'll go over in a bit. And this can basically be fed into all these different methods in Q-Chem with no extra implementation required. And you can get your property with finite difference. Right, so from this, our new capabilities that we added in the Q-Chem 6.1 release, we now have double hybrid DFT, various methods in libgPVT, including regularized MP2, regularized orbital optimized MP2, MP3. We have calculations of available of NMR shieldings and the magnetizability tensor. The CCMN2, so the couple cluster, is still underway, so maybe next release hopefully. Right, so what do we actually need to implement for these additional terms that I alluded to. So first we look at the field Hamiltonian, which with explicit dependence on our field terms. So first we'll look at our sort of base electronic Hamiltonian. We have the momentum term, the nuclear attraction term, and then the electron repulsion term. We replace the canonical momentum with the kinetic momentum, which now includes effects from these vector potentials arising from the external B field and the nuclear spins. So simply blow up the square, and we get all these extra terms from the square of the kinetic momentum. So first, again, it's just the original kinetic energy. And then we have these two terms that only depends on the B field. So you have the first one is called a paramagnetic shielding, which is linear in B. And then you have a diamagnetic magnetizability term, which is quadratic in B. So these two terms is what goes into the magnetizability calculations. This third and fourth term, we have the paramagnetic spin orbit term. So it's linear in nuclear spin. And then a diamagnetic shielding term, which is linear in B and in M. So now you can notice these terms have this 1/r³ dependence. So it's a little more complicated. And lastly, there's a diamagnetic spin orbit term, which is quadratic in M, the nuclear spin. So this term goes into the calculation of the J couplings. So this is actually still underway. Hopefully the next release will have it. Right, so the next piece in the integrals is this gauge origin problem. So because we're now dealing with these vector potentials, we took the curl of the vector potentials, we can add a scalar function, and this does not change the corresponding B field that comes out. What this means is that the vector potential A is not uniquely defined. So this is not an issue when you have exact wave functions, because your Hamiltonian transforms the same as the exact wave function. So your expectation value, so energy and your properties does not change with this gauge transformation. This is not true, however, when you don't have an exact wave function. So for example, if your basis set is not complete, then your NMR shielding calculated will depend on the size of your basis set. So one way to tackle this is with this GIAO approach, where we explicitly account for this gauge origin dependence by appending sort of a phase factor term to our original GTO. So this phase factor gauge function effectively shifts the gauge origin of each basis set to its center, with the effect of making our corresponding GIAO basis function complex. So this correspondingly makes all of our matrix elements complex. And we've implemented these in Q-Chem. So a little quick side note on how these are actually calculated. So these four new terms that we need for nuclear shielding and magnetizabilities, these are done in a similar way as how you do it, the kinetic term. So in effect, the operator, what it does on your basis function is it leads to raising, lowering of its momentum. As a result, you get sort of these linear combinations of a base integral. So for the paramagnetic shielding and the diamagnetic magnetizability terms, you have sort of 16 and 18 overlaps, summing up to give you define a matrix element. For, yeah, so something that looks like that, where you have S that denotes the overlap. You have sort of these various momentum shifts, and you sum up to your final matrix element. So for the other two terms with the one of our cube dependence, we use the base integral as a field integral, which looks like that. It's sort of x over r cube. So what this looks like is you have, so for the x component, so this 1/3 of your matrix element, you get sort of 4 terms. So in total, you get 12 terms for the diametric shielding matrix element. Right, and also now the other terms in your Hamiltonian, the nuclear attraction and electron-electron repulsion, they also evaluate GIAOs, so they're also complex. Right, so in effect, we need a complex implementation of a methods in Q-Chem, which a lot of them have, so we can just leverage those and get our properties from finite difference. Right, so sign off here. Having now the energy explicitly depending on external fields, we can sort of just simply calculate all these properties by finite difference with really no extra implementation. Of course, there's a question of numerical accuracy always with the finite difference approach, especially when you get up to third and fourth order. Yeah, so the workflow in Q-Chem to calculate properties using this GIAO formalism is quite simple. So you first spawn a number of single point jobs corresponding to the order of accuracy you want in your finite difference. These jobs get fed into your corresponding package. You have, for example, Hartree-Fock, you get libgscf, DFT, libdft, and then MP2, you get libgmpvt. After these energy calculations are done, these are collected by the num-deriv module, which computes the derivative from finite difference and then prints out the results. Right, so how to actually run this job is we made it sort of try to be as user-friendly as possible. So we've created 2 new job types, NMR shield and NMR mag, corresponding to nuclear shielding and magnetizability tensor. So now we have various methods you can use with this: Hartree-Fock, MP2, regularizable MP2, or double private DFTs. Right, and then you have the step size of the finite difference, both in B and M. So these can be tuned to optimize the numerical accuracy. And then we have sort of 3 variables that are just required at the moment. So our code is only routed through GNCM and final, so we have to turn that on. Integrals are only implemented in libqint, so we also want to use that. And then 2 sort of features which are quality of life features. So one is doing only the diagonal elements in your shielding tensor, if you're only interested in the isotropic value. So you can turn that on. You can also select a nuclei index that you're interested in for the shielding calculation. So these are 0 indexed. So this sort of saves some work if you don't really need the shielding from the protons here in the water. Right, so what comes out of this calculation is this prints out the end. So this is the NMR shielding output example. So first we have the first part is for each nuclei, we print out the full tensor. And then we print out the isotropic contribution. And then we have the second part at the end, which is a summary. So if you do more than one atom, here you have just the isotropic number and also the anisotropic number if you're doing the full tensor for each atom you selected. Also, side note here: if you're interested in every atom, you can just not do the shielding input section. Right. So now let's look at the finite difference accuracy of these methods, which is a sort of quick concern when you're doing anytime you're doing finite difference calculations. So first, we sort of benchmarked Hartree-Fock magnetizabilities with double zeta basis functions. Right. So in fact, here, because we're doing second order finite difference, you get increased numerical error when you get the step size to a smaller value. When you go to a bigger step size, you get sort of contamination from high order contributions. So we have a sweet spot here of 1 - 3 in the B field, where this is percentage error. So it's really quite good. This is 1 - 4 in percentage error. On the other hand, with the shielding, so now we have 2 step sizes scan over. The second order finite difference doesn't do as well, but still pretty okay, right? We have 1 - 2 order in the percentage error. When we blow it up to fourth order finite difference, so where we do 48 single points instead of 12 single points, you get this 1 - 6 percentage error, what is pretty good. Right, so this sort of validates this approach and using finite difference to calculate properties with sort of okay to minimal loss in accuracy. Right, so next I'll talk about just some quick examples that we've used this code for, mostly focusing on perturbation theory. Right, so first we looked at magnetizability using a sort of small molecule test set of 27 molecules. They include so the first row heavy atoms. Yeah, so what we're looking here is a study in regularization of the regularized OMP2 method and the regularized MP2 method. So we look at here, the green line corresponds to the Hartree-Fock error with respect to couple cluster singles and doubles with parentheses triples. The red line here corresponds to the non-regularized MP2. The blue line corresponds to the non-regularized orbital optimized MP2. So we observe here that the regularizer really does some good work in reducing the errors in both the MP2 and OMP2 methods. A side note here, these do not reach the error of couple cluster singles and doubles, which is a bit expected since we're a little bit cheaper method. Right, also looked at shielding using the same data set. So now we have these numbers of data points, which is of course quite small. So this is an initial example. So we've looked at first the regularized MP2 using this Kappa regularizer formalism, where we modulate the denominator here, which is the energy gap. So this avoids energy divergence when your gap goes to 0. So for so for proton shieldings and carbon-13 shieldings, specifically using a larger value in kappa, so this corresponds to a weaker regularization, we sort of observe close to and better than CCSD level performances. And for the nitrogen-15 shieldings, we observe quite a significant improvement over CCSD. So this was quite nice since we were looking at a non-iterative N⁵ method in regularized MP2. We also looked at a sort of MP2.x method, which is adding in a scaled down MP3 energy contribution. Right, with MP3 now we have into the sixth method, so we're same scaling as CCSD. So in this plot, we are showing dotted line is the CCSD error compared to CCSD parentheses T. Yeah, we see that for all of these nuclei except proton, adding some amount of MP3 contribution gives us quite nice results. We outperform CCSD in most of these nuclei. Right, so in summary, getting the explicit field-dependent energies allowed us to calculate basically any electromagnetic property of interest with no additional implementation. It was a nice result that the finite difference procedure did not produce large numerical errors for second-order properties in particular. Using this formalism, we'll be able to calculate really a lot of properties in Q-Chem with basically just specifying the energy derivative that you want and what external perturbation that you're interested in. And lastly, looking at some methods in lithium PPT, we found that all of them improved upon MP2. And for shieldings, some of these methods improved upon CCSD, which is quite nice. And this shows the promise of leveraging these various new methods in Q-Chem for property calculations. Right. And a bit of new development here. Recently implemented the analytical first derivative of energy with respect to the nuclear spin. So this goes back to the earlier slide where we showed that for variation methods, calculating first order properties is really simple. So having this nuclear spin derivative calculator implemented, we can now do the nuclear shielding tensor by one order of finite difference. So the B derivative we do by finite difference, the nuclear spin derivative we do by analytical manner. So this led to really vast improvement in the numerical accuracy, right? There's 20⁻⁵ and percentage error just doing a second order finite difference. So this will be quite promising going forward. This also, reduce the number of single point calculations needed. Right. So the roadmap ahead for the rest of this module, we would like to complete the DSO integrals, so the diamagnetic spin orbit integrals, so we can calculate J couplings. We also have to implement this interface with CCMan2, so we can get couple cluster NMR shieldings going in Q-Chem. And then, of course, we have a new avenue of calculating these new property of interest using our finite difference approach. We also would like, especially for Q-Chem developers, a better number of implementation, which further leverage parallelization to reduce the dwell time of our calculations. And yeah, that's it. Thank you everyone for your attention and patience with the sound issues.
Awesome, thanks so much. Thank you for an excellent talk. As I mentioned earlier, there is a questions section sort of towards the bottom. If anyone has questions that they would like to ask, please feel free to do so now. Because I do think we still, in fact, have a little bit of time before we're supposed to wrap up at 11. So, great. Well, if nobody else has questions, actually, I should go ahead and make you the presenter again. Sorry. That way you can go back through your slides. Yes. Okay, so there is in fact a question. which is what are the pitfalls of these methods?
So this is specifically about the perturbation theory methods, I assume. I can actually see the.
So, well, it's not specified. So it could be talking about if the person asking this question wants to clarify which methods they mean. They I suppose could either mean the MP2 method or the perturbation theory methods, or the whatchamacallit, like the analytical versus numerical, like what the respective drawbacks of those are.
Yeah, thank you, Sharon. Yeah, so first for the numerical versus analytical approach, the drawback for the numerical obviously is always you have the question of numerical accuracy, but as I've shown, it's really not a big concern for second order properties. Another drawback would be basically just more computational resources needed, right? We need really 12 single point jobs of energy calculations compared to one job of response equations calculation. But considering sort of the wall time perspective, right? So these jobs basically don't depend on each other. They're just independent calculations. So they're really simple for parallelization. So in the wall time perspective, you're really just waiting the time of one energy job. And you can argue that you can really skip the response equation solvation part, right? So I think it's really competitive if you have multiple computation nodes available. For the perturbation theory methods part, right, one obviously is the cost, right? It's higher costs compared to DFT, right? The MP2, which is the cheapest one, scales at n to the 5, right? DFT usually scale n to the 3rd. But in some cases we can get really high accuracy than DFT. I guess here I'll show a backup slide here. So this is a paper from 2012 benchmarking basically a whole bunch of DFTs versus MP2 Hanshi-Fock. So here we see that so here I guess we just look at the black diamond, which is the air of all nuclei. So top part here you have your LDAs, GGAs, but the GGAs, hybrids, and the very bottom you have double hybrids. So just looking at the black diamond, so you see really that MP2 really outperforms the rest of DFT except double hybrids. So that's part of the motivation of doing the study on the perturbation theory methods and getting the double hybrid DFT in Q-Chem going to calculate the nuclear shieldings.
Okay.
I hope that answers your question.
I think so. Yeah. Good answer. Thank you. I guess there's a couple other questions down here as well. The person says thank you for the question and answer. So, and then we've got a couple of additional questions. The first one is, would extension to unrestricted MP2 be non-trivial for analytic implementation of these properties?
Right. So this is, I assume, it's about the numerical approach. So actually, we already have generalized MP2 and corresponding MP3 and OMP2. Those are implemented because you need generalized instead of restricted to calculate J couplings. So those are ready to go. The unrestricted is also implemented, but it's not fully debugged, I have to say. So really the advantage here. Oh,
sorry, I think this person was asking about the analytic implementation rather than the numerical.
Oh, okay. Right. So the implementation side, I assume, is the same amount of work with the restricted implementation. Once you have the equation derived, then usually the unrestricted is just some extra terms on top of the restricted.
Okay.
So again, it's just someone just has to sit down and do it.
Yeah. It's just a matter of, going through and deriving it. So, okay, that makes sense. Thanks. So, and then we have one other question of, kappa OMP2 calculation itself is fairly costly. So how expensive are these shielding calculations?
Right, that's a great question. Yeah, so kappa OMP2, yeah, so it's a sort of iterative n to the 5. Yeah, so it's sort of in the, I'll call it a medium expensive method, right? We live in between DFT and a couple clusters. But it did offer, improvement in accuracy. So it's a good trade-off, really. In practice, it'll take, for the system that we study on, it took probably around 10-ish times longer than the SCF part. So one can consider the accuracy trade-off with the waiting longer for results.
Okay, that makes sense. Cool, thank you. I don't suppose anyone else has questions. Let's see. Someone's talking about the K value, perhaps, or the kappa value not being trivial. But yeah. So if no one else has any additional questions, it's about 11 o'clock, so it's about time for us to wrap up. But thank you again, Jonathan, for such a wonderful presentation, despite the technical difficulties. Thank you to all of the audience for their patience and sticking it out with us through the audio hiccups. And thank you very much for the, I've learned a lot more about NMR shieldings today. So, additionally,
yeah, thank you for having me, and yeah, thank you to the audience again, for listening.
Thank you. And just a reminder, if anyone has questions that they wanted to ask but didn't get the opportunity to, there is always the Q-Chem forum. We've posted a topic about this webinar. If you have questions that you would like to ask, we can always ask those there. So thank you very much, everyone, and we'll go ahead and wrap it up. Take care, everyone. Have a great day.